Okay. Thank you all. In the interest of time, I think, there's been a couple of good posts. They were included in the meeting invite. So the assumption on this meeting is that people have read at this point Vitalik's post as well as Donkrod's post, the two that were in the invite. And the goal in this discussion, I think we wanted, so Piper and Joseph and I were talking about having this discussion to level set people to get to a higher level of understanding of Verkle trees, especially given the dramatic change of the economics of witness sizes, which is a pretty fundamental game changer for the kind of options to do in statelessness. And Vitalik's post also, I think we're going to talk about Verkle trees first, but Vitalik's post also had quite a few things about the trade-offs of expiring state and some of the edge conditions on retrieving it. So it's a little bit orthogonal to Verkle, but hopefully we get to that as well. So I think I'm going to hand this off to Donkrod here. I think, judging from last time you gave a talk, Donkrod, I think probably the focus on the engineering view of the Verkle trees is the most useful, given the time frame that we have for this meeting. Vitalik, you unmute.
Yeah, state the mathematical assumptions, but then move on to the engineering, what we can do with those assumptions.
Right. Okay. I thought Vitalik wanted to give a presentation on Verkle.
Yeah, no, I do have some slides, but
okay, yes.
There's also not too many slides, and I'm happy to, Dankrod, feel free to kind of jump in whenever as well.
Yeah, sure. Yeah, I haven't prepared.
I am going to just share the screen. Do people see the shared screen?
Yep.
Yes. How many ghosts are there?
We got two ghosts.
Good question.
Two ghosts.
Confirmed.
Well, plus all the ghosts we can't see.
Right. No, just want to confirm people actually see and aren't just falling for the verifier's dilemma. Okay, so Verkle trees, right? So starting off, kind of what is a Verkle tree? So the high level goal idea here is that it is a data structure that serves the same function as things like Merkle trees and Merkle Patricia trees. And it tries to combine at least some of the benefits of trees and cryptographic accumulators. So when I say trees, I mean things like binary trees and hexary trees and Patricia trees and AVL trees and that whole family. And when I say cryptographic accumulators, I mean like either Kate commitments or some like RSA accumulators or like any of these fancy mathematical constructions. So Verkle trees try to be a kind of compromise in the middle of these and have a lot of the good properties of both accumulators and trees. So a Verkle tree is a tree of Kate commitments. So you have a tree and each node in the tree has a width of, in this example, 256, but really it's a number that you can set, like it might be a good idea to make it be 1024 or 2048 instead. It's just a trade-off between kind of witness size and proof generation time, basically. But 256 is a good number, so just like mentally, we'll just stick to that value. So kind of on the right here, you have a little diagram. If you want to stick the word cat, dog, hippogriff, and hippopotamus into a Verkle tree, then each one of these nodes would just represent a letter of the alphabet. And then you would have leaf nodes. In this particular structure, we don't bother with extension nodes. We just only have leaf nodes, and so you do have a bit of a kind of single child extensions. But in a realistic kind of randomly dispersed account setup, like you'll probably end up having around like 4 layers of this and then a bunch of leaves. So assuming the values are randomly distributed, a path going down from the top to one value will only take the logarithm base 256 of n. So this is 8 times fewer nodes in the path going down compared to a binary tree. So for example, if the state size is around 2 to the 32, which I think is a good estimate for a medium-term size, then like you can go down in 4 steps, whereas in a binary tree, you can go down in 32 steps, and a hex tree can go down in 8 steps. Now, of course, there is a problem with having a width of 256 if you just use a regular hash tree, right? And that problem is that if you want to have give someone a Merkle proof, then you're sure you can give someone 4 nodes, but each of those 4 nodes will have a width of 8 kilobytes. And so your proof is just going to be crazy long. And so this is where the Kate commitments come in, right? This is why we want to use Kate commitments for each of these nodes instead of just making the root be the hash. So Kate commitments, Dunkrat has an excellent presentation I'm linking to. There's that QR code is also a link. Basically, they use elliptic curves and polynomial math to create a data structure where the inclusion of any subset of values, so you can include, like say, up to 256 values, and really it could be any number, but the inclusion of any subset can be proven with a single witness, right? So if I have this object and I want to prove that this, like the number 1 is at position C, the number 2 is at position D, and then some hash is at position H, then I can just provide one single elliptic curve point, and that can be used to verify just all of these values. You could even go further. So this is this multi-proofs protocol. Basically, if you have multiple commitments and multiple leaves, and this could be an arbitrarily large number of commitments and leaves, you can make a single proof, like less than 200 bytes, that proves the membership of all of these values. Right, and there's another linky there that you can kind of click or scan on if you want. So basically, this gives us so the witness size, the actual witness size here, right? Like it is going to consist of if you want to prove a value going down here, just the commitments that go along this path, right? So you don't have to provide all the nodes. Instead, you provide this commitment over here at the top, then the commitment that is the letter H, and the commitment of the letter I, then the letter P, then the second letter P, and then the O, and then the P over here. You'd have this kind of series of commitments, but each of these commitments is only 48 bytes. And then you just slap one proof to the end that says, well, each one of these values actually is in the correct position of each one of the other values. So multi-proofs are amazing, right? And now hopefully you can kind of see how these witness sizes become smaller, right? Like basically, instead of being 8 kilobytes times 4, you would just be 48 bytes times 4. Now, this is the other important thing, which is why we need to compromise, right? So why bother with trees of commitments instead of using one Kate commitment for the entire state? So there's 2 problems with using a big Kate commitment. One is that it requires a very large trusted setup, and very large trusted setups are very insecure, right? So for the scheme that I'm suggesting here has a trusted setup size of 256, right? And so if we want to, we could literally just do a size 256 trusted setup, and that is so easy that you could just do it all in JavaScript, and we could get 50,000 people to participate. But if the trusted setup goes up to a size of the entire state, so a size of 8 billion, then well, good luck getting more than 10 or 20 people to be part of it. And so basically, trusted setups are not binary, they're qualitative, and it's the problem is much less bad in the n equals 256 case than it is in the n equals 8 billion case. Problem 2 is that computing a witness takes O of n time, right? So computing one of these multi-proofs or even a single proof takes an amount of time proportional to the size of this whole thing. Now, it turns out there is a protocol where you can compute all n witnesses in O of n log n time. But if you use the pre-computation trick, then even a single state update, so if there's a block and that block changes a value, it requires you to recompute everything, right? So basically either reading is O of n or writing is O of n, and you're kind of stuck if you just kind of use one pure Kate commitment. So Verkle trees are a nice compromise, because if you just have a tree of commitments, then instead of this O of the n here, instead of being n being the state size, it's just O of 256. And it turns out that with a bunch of optimization tricks, like computing a witness actually is quite fast for a tree of commitments. So witness sizes, right? So a Verkle tree witness going down to multiple values requires one, the actual data, right? So like, let's say if you're proving, I don't know, hippogriff and dog, you obviously need like the key, the value, the key, the value. Then you need all intermediate Kate commitments. So in this case, you would need like the letter D, then you need like G, O, P, P, I, and each of these things are 48 bytes. And then you just need this one single proof that's like a bit less than 200 bytes that just proves that all the relationships between all of these and that all of them are correct. So here's just an example estimate. So assuming a state size of 2 to the 32, and assuming you're proving 5,000 keys, which actually is approximately the post EIP 2929 maximum, not including code. So we do want to add a gas cost for accessing like individual chunks of code at some point, but we do not have this yet. So assuming these numbers, there's three, like if it's 2 to the 32, right, then like roughly you'll have 3 levels of intermediate commitments, right? So the first level, so 3 levels basically are like you have the root, but the root doesn't count because you already have the root. First level has 2 to the 8 commitments. The second level has 2 to the 16. The third level has 2 to the 24. And then the last level that has 2 to the 32, well, that's like really your data. Now, in practice, it's not quite so clean because like you might have more collisions in some places than other places, but like it's roughly about like this, right? So if you're proving 5,000 keys, then on the first level, well, there's all 256 commitments will be part of the proof. On the second level, you have a bit less than 5,000 because there's a bit of redundancy. On the third level, you'll probably just have 5,000. And so in total, you have about 10,000 commitments, about 480 kilobytes. The data itself, 160 kilobytes. Actually, this is a bit of an underestimate because if you have keys and values, then like you actually want the 32 bytes for the key and also 32 bytes for the value. So this should actually be 320K. Proof 200 bytes, and so the total is going to be about 800 kilobytes, which is only like about 2.5 times as much as the theoretical minimum, right? So witness size properties are amazing. Witness generation and verification. Degra, do you have numbers for how long generation and verification take?
Oh, I have a sheet. Yeah, if you continue.
Okay. Yeah.
I can find it.
Right. But like basically, it's easy to provide. It is very possible to generate these witnesses. It's very possible to verify them. There's I think 2 kind of nuances that change from an Ethereum client perspective. One of them is that these trees are very wide. And so like storing them in the database the way a lot of existing Ethereum implementations store them in the database is dangerous because like every time there's an update, you would have to store the old thing and the new thing, and you'd be duplicating 8 kilobytes. And so like there's 2 ways of fixing this, right? One is to kind of at the database layer, use some kind of like layer on top a tree structure that has a lower width. And then another approach is this thing that I made a quick proof of concept of, which is like basically just updating in place. And then the second nuance is from a kind of like sync protocol perspective, and from a witness provision perspective, right? Like basically in a tree structure, in a traditional binary or hexagon tree structure, providing nodes and providing a witness are the same thing. Whereas here, providing a nodes and providing a witness are not the same thing. Right. And I do think that with things like Snap Sync, we are kind of moving toward having a distinction between the 2. But generally, right, like if you want to help someone sync, you provide the intermediate data. But if you want to give someone a witness, then it's better to just have an explicit protocol, and you give someone the intermediate commitments, and you give them the proof, and they have a witness. So that's the kind of prepared presentation. But, I'm happy to also answer questions if Degrad, if there's anything important that you think that I left out.
Right. So I just posted my statistics from this is my Python proof of concept. in the chat. So I mean, I would expect that can be accelerated by quite a bit because I didn't try very hard to optimize field operations, and that's the main work that has to be done there. And yeah, to like, so it's all measured in seconds basically. So as an example, if you go to the 2 to the 20 keys tab, where 1 million keys are basically inserted with a width of 256, then the time to generate 1,500 keys is a proof of 1,500 keys is 3 seconds, and checking this proof was about half a second.
I mean, intuitively, do you expect a 10x speed up in an efficient language, if not way more, due to optimization?
Right. Yeah, we have to be slightly careful because the main operations are the field operations, and Python does have like a reasonable big implementation. So yeah, I mean, maybe 5 to 10.
Actually, one quick question with those numbers. Were those numbers using a width of 256 or 2048?
256, that's what I
Okay.
just put it. So they're all in the sheet, right? It has, I varied the width, so we can see, like, for example, for 10 bits, like the time to check it goes down very slightly, but the time to generate the proof goes up a lot to 11 seconds. But you would mainly, like, yeah, more bits would the reason to go there would mainly be to get smaller proofs rather than to get faster verification.
I have a question. So in our current like hexarray patricia tree land, we've got like 5 years of people figuring out how to work with the tree in a way that's efficient and fast. Today, kind of landing on flat database layout stuff that kind of treats the intermediate part of the tree as ephemeral, and it's just sort of the things that people have figured out how to work with the hexarray patricia tree and still be fast. Do you guys have a sense for like the performance hit we might take as we switch into this new like paradigm? Like where's the scariest part of the performance of this? With respect
I mean, I'm not a database expert for sure, but my question is why is the database layout and the so we basically have two things, right? We have a database layout where you actually want to access stuff, and we have this authenticated data structure where you want to prove stuff to a verifier. And the more I think about this, the more I think these two are mostly orthogonal. So I think this was like basically the big mistake with the hexarray tree is to like think that the data structure, the authentication has to be aligned with the database, but actually this is not the case. If you think about it from the beginning in that way, then yeah.
Agreed, because that's where the efficiency gains came from in the hexarray patricia tree. I think a lot of it comes down to keeping, if you treat them as separate, then you have to keep them synchronized with each other perfectly. Otherwise you, can end up with a very fast database that doesn't actually represent the real data.
Right.
Yeah. And I think that there's, my guess is that there's a learning curve that's going to come with this.
Yes. Mm-hmm. I think so. Yeah, I agree. I guess like the interesting thing would be like if some of the more cryptography oriented people would work together with like the database optimization experts, and then together we could figure out like what we need to do. Like I agree. So there's definitely like there will be it's a big re-engineering of everything, right? So like there will be lots of engineering problems to solve. I haven't seen anything yet that can't be solved in my opinion, but that's obviously
my intuition. I kind of didn't expect like a detailed answer because I think it is one of those things that there's just going to be a bunch of engineers who have to get their hands dirty and figure it out. Same way that, okay.
I think Vitalik has started doing some implementation of a database for this.
Right. Well, I did that POC that I linked to, I think in the post. Like basically, I think one of the considerations is just that like Verkle trees are more amenable to kind of editing things in place and somewhat less amenable to like just using the hash as the key for things, because that'll just require like pushing a lot of data around.
Where are you guys at on having any concept of like a spec or test vectors so that we could start getting implementations like beyond research going? Because that feels like one of the big things standing in the way, at least, of being able to start trying this and using it and seeing what it looks like.
I do not. I think, Guillaume, have you thought about directly like Verkle tries in ETH1 yet, or is it so far just Verkle tries in general that you have started implementing?
Yeah, the goal is indeed to start using the whole snapshot, so all the key values from the main tree. I'm doing the implementation to this end. Yeah, I'm just making sure that it works before I run it into the main. Yeah, getting all the mainnet like the data, the key and values from mainnet. But yeah, when it comes to an actual test vector, yeah, something smaller. I mean, I could produce something if you're interested, but so far there's nothing that I can provide.
Okay, right. So I think like one of the things that we haven't made a decision on yet, what's the best, is kind of this question. So one of the things that you can get rid of if you want with Verkle trees is extension nodes, which you need in binary trees because like you very often have like lengths of keys that are the same over several keys. Whereas in Verkle tries, that's just quite unlikely because each time you go at least 8 bits deep, maybe 10, depending on what width you choose. So like the normal inner nodes are kind of their own extension nodes already in a way. But then if you don't use extension nodes, then basically like you can't do this trick where you make several keys for the same account that are very similar at the end, because then your try suddenly has full depth. So that's one of the things we need to think about, what's the best way there, or maybe actually do a couple of experiments to know which one is kind of the most promising solution. But otherwise, I think, I mean, there's not much in the way of writing something similar to the binary try EIP now, and being very concrete in that. I think like it's, yeah, it shouldn't be too difficult to spec that out, but it hasn't been done yet.
I had one question on the statelessness side of generating new proofs. How much of the additional data on each 256 element Verkle group do you need in order to generate a new proof? Do you need to actually have accessible to you the other
all the siblings? You like the way okay, so there are different designs. You can make a slightly less efficient design with this whole thing, where you don't need the siblings to generate. Well, you don't need the siblings to aggregate proofs. You need to them. So that would be more of a kind of like design where you optimize for proposer statelessness as well. I don't think that's very good. I think like we should like, it's a bad idea to optimize for proposers so much, and we should just like hit them with the cost of this, because it's really not that much. Like it's quite doable, as I showed. Like, I mean, it's really a few seconds, and you can do all kinds of optimizations with parallelizations and so on. So like, I would say like just assume that the proposers like do this, and yeah, be done with it. Is my opinion here, and that will save us a lot of like other problems basically if we can do that.
I'd like to ask.
Can I restate that real quick just to make sure I understood what was asked? That for like a single node in the tree that has 256 child nodes, I don't know, that in order to generate like the proof as you walk down through that, you need all 256, and then you generate the 148 byte proof, and that's all that you need to prove that level.
Right,
Okay.
but let's be more precise. So the node, right? So you have there are two parts of the proofs, right? Like if you go back to the picture, like basically you need to give all the intermediate commitments of all the inner nodes in between, right? All the branch nodes. That's one thing. Those commitments you have, right? Those you would just store them. There's no need to recompute them all the time. So that for that part you don't need the siblings. But then there's a second part where you compute all these Kate proofs, where you like for each commitment you show that it is the child at index I of its parent. And for that, the way we've currently constructed it, you need all the siblings. You need,
One, I guess, question for database people is like, is it bad that you need all the siblings? Like one important assumption that I'm going off of is that like hard drives have page sizes of like 4 kilobytes. And so grabbing a big chunk is not really significantly more expensive than grabbing 32 bytes.
I think that's true.
That big chunk being 256 48 byte commitments, right?
It's actually 256 32 byte hashes of commitments, but yes.
Okay.
Right. Well, you could do it either way, I think.
Yeah.
I'd like to ask a question that Chad is getting to. It seems these numbers are useful for, so we have numbers here for how long it takes to generate proofs and to verify them. But if remember right, Kate commitments take a while to actually create the commitment. Like how would this impact like block proposers?
How will this impact block proposers?
People who are actually like making the commitments.
No, they
Right.
like to make the proofs. The block proposers make the proofs.
No, I think the question might be like, what is the cost of updating in response to 5,000 writes?
Right.
Right. Yeah. Like making.
Which, by the way, everyone has. So this cost is well, everyone will incur, not just
Right.
proposers.
Fair.
So I think we can compute this right now, right? Like the way that the storage works is that we just store the commitments at every level, right? And so if some 5,000 leaves get updated, then there's 20,000 commitments or maybe like 15,000 commitments that needs to be regenerated. And actually, no, we did the math.
They don't need to be regenerated.
Right,
That's
exactly. They just need to be
it's
updated.
only one elliptic curve exponentiation per update.
Well, no, like no, to generate a witness, there's only one, but to update and respond, like to update all of the commitments, you need to do 10,000 separate exponentiations.
Yeah, that's right.
Right. So like basically updating is a bit more expensive than reading because doing a size 10,000 linear combination is significantly cheaper than doing 10,000 elliptic curve multiplications separately. But stores are already at least 2 times more expensive than loads, so the gas schedule already accounts for that.
Right. So basically 5,000, if we assume that 5,000 reads is the max, then it would only be 2,500. Right.
Right.
Yeah.
Do we have a number off the top of our head for how long a single elliptic curve multiplication takes? Like it should be, I believe it's like in the low hundreds of microseconds, right? Or even lower.
One experimentation is 100 microseconds, roughly.
100 microseconds, right? There we go. So multiply that by 2,500 and you have 250 milliseconds.
Well, for every node in the tree. So multiply that by another 3 or 4.
Oh, yes, you're right, because we're doing 10,000 of them, right? Yeah. And this is a worst case block that's doing like just entirely writes, right?
Yeah.
Did those numbers come out to about 1 second there? We're talking.
Yeah. So worst case is 1 second.
Is that like after all optimization, or is that like as we stand today?
That is fairly optimized. Like we are talking about using a good library, so that's not like Python code basically. I don't want to say there are no further optimizations, And I guess like this is something I haven't thought about yet. If you can optimize writes further, there may be tricks by which you can prove
You can
that you've done
multi-thread.
this. Huh?
You can multi-thread it.
That for sure, yeah. But maybe you can also let the prover generate something that makes verifying writes easier. I haven't thought about it. It's certainly possible, but like basically you want to prove that you have done some updates. I don't know. It seems very possible that there are large optimizations there, or that maybe like, let's say like that you could get it down to a similar cost to a read.
How sure are you guys about this stuff? I know it's kind of like a weird, like abstract question, but like, is there something else coming on the horizon that's like, oh look, this is better again?
So we've definitely agonized over this question for a long time, and like we
this
have
is also why this is coming so late in a way. Why? Because we're like always there should be something better, I guess. Yeah.
Right. Like the things that we've like we made that kind of open call for better solutions on the research. I mean, I even reached out to Dan Bonnet asking if he has something better. I think the general feeling is that in the 5-year horizon, like, or whenever we end up wanting to do a post-quantum switch, we will have binary trees with, and that can be the same code that's like that the binary tree people have already written, but just replace SHA-256 with a Stark-friendly hash function and then do a Stark over it. But like this technology is expected to be about 5 years away from being safe. So
basically there's like, so we had the like hexarray tree to binary tree where we had like efficiency gains just from, not having as many siblings. Now we're looking at Verkle trees where we get efficiency gains by effectively omitting all of the siblings, right?
Yes.
Like now you get that efficiency gain, and then the long tail efficiency gain that's 5 years off is basically omitting all of the middle stuff, right? And getting kind of like a fixed size witness plus the leaf data.
Yep.
Okay, and that's a ways off.
Or potentially then 10 years you don't even need the leaf data because you can Stark everything. But yeah,
magic.
Yes.
Okay.
But for now we need the leaf data. Yeah, I think like in addition, so like there's two things we're unsure about. Like right now, the performance of the Starks is just not there yet. Like it's still like a huge amount of computation that you need, which would really like,
I think that they got to like Starkware did get to like proving 10,000 per second on a GPU, right? So like if you require block producers to make GPUs, then like that you would actually be able to generate a witness for a block in like about like 5 to 10 seconds. The problem is that this is using exotic new arithmetic friendly hash functions, and we just want to wait a couple of years for those to get cryptanalyzed.
Yeah.
And so it is y'all's opinion or not that we should skip binary tree and go straight to this? Is that the kind of assertion or suggestion?
I think if we want to go to Verkle trees, I think skipping binary definitely makes sense. Like
yeah, it makes more sense the other way around actually. Like it's kind of better, like Verkle tries are better as this intermediate solution before we are ready to like get full witness compression. Basically Verkle tries will allow us to do the statelessness now. And we just can't quite get there, or it's like really difficult to get there with binary.
Right.
Actually, I have one more question on that, and then I noticed that Paul has put up his hand, so we'll let him ask that as well. But just because it's related to this one is, so the reason we wanted the binary tree was that it had the property of Patricia tree that every hash had a specific location to find it. Is that the case with Verkle tree as well? Because I didn't see you talking about it going down to the full 2 by 2 to the 256 possible elements.
No, the tree does, like, it is a trie, right? So it does, like, if someone comes up with keys at positions x and x plus 1, then like it does go up to having 32 levels. but like doing that is hard because it would require you to like basically do 2 to the 256 work to actually find those hashes.
Okay.
So like every read like assuming randomly distributed addresses, every read corresponds to like about 3 intermediate steps. Assuming a adversarially generated addresses, it would go up to about 6 intermediate steps or maybe 7.
Okay. Okay, and Paul, why don't you chime in now?
Yeah, maybe it was explained already, but I missed it. There's a pre-state and a post-state that has to be proven, and there are writes, of course. You know, if you're only reading, you just have one sort of proof for everything that you're reading. But then some of the things you're updating or you're inserting as well. There's this strange thing where there was a node there, there wasn't a node there. You have a proof of exclusion in the pre-state, and then you have a node there in the post-state, and also deleting things. There's all of these strange things. Are all of these sort of numbers that we saw, I think it was 600 or 800 kilobytes, do they include, because I imagine the post-state would need its own, you know, Verkle tree proof. There might be some deduplication.
Well,
but
okay, here's what you do. Like basically, all of these, so like they work all very similar to binary Merkle trees. It's all very, very similar. You just have to like basically go up the try and like recompute commitments, and you always have to do one exponentiation basically for every update. What you're going to do is basically that for the writes, like you basically have to add some extra reads potentially. So for example, for every write that adds a key, for a write that overrides a key, that's trivial. Like that's the easiest case. If you add a key, then you have to basically add something to the proof that somewhere is 0, basically where you want to write that is currently 0. And when you want to delete a key, it becomes slightly more complex. Then you will have to like, you have to add some extra things because there are some complications about what happens when one node goes down to having only a single child, which is when we want to remove the inner node and propagate that child upward, basically in the try. But they are all doable. There are some complications, like, but yeah, basically you can think of it like to write something, you will add some extra nodes to your reads basically, and then when you do the write, you check that those were like added, and you can then do everything.
Yeah.
Just to
By the way,
chime in-
Tancred, I just
sorry, go ahead.
and send you a comment. Like I think you actually can optimize the writes because you're only multiplying by 1 of 256 Lagrange points, so you can just store a big pre-computation table. So I think we
All
can
right.
shape.
That's one thing. That's nice. Yeah. Mm-hmm.
It's just to briefly point that out though, because I actually had the same question earlier, but I think I kind of so I think the point is that basically you don't need a proof for the post-state correctness, right? Because the verifier can also just update the commitments themselves. So you don't need to have any proof over the updated commitments, but like every verifier just updates the commitments themselves. And yeah, I think that's important. So yeah, no proof
It's
necessary.
very similar to binary Merkle tree, basically, where your write proof is basically you do already have all the nodes and you just update them. Yeah.
Well, but wait, for like a normal binary tree, you would need the siblings though, right? And like for Verkle tree, the difference is that the verifier doesn't need the siblings and can still do the update.
But think of the siblings as the proof.
Yeah, okay. Sure.
There's the obvious question of throughput. I think, by the way, before I ask this, Dankrad did an excellent job with his work with speeding up the computations. It was excellent. There was changes of basis and all of the standard sort of applied math tricks that people know, but Dankrad creatively applied it here, I think. And the question is with throughput. I think the two leading candidates, it's sort of Verkle tree after this meeting is obviously very, very strong now. But the question is throughput. If we compare regenesis as Alexei's numbers show versus this, I'm curious which one would have more, for example, simple transactions per second.
Right. I mean, I think like the thing is regenesis doesn't directly, like you could do regenesis with Verkle tries, obviously, right? So that is not, I guess that is not the right question. The question is like, what we want to push for is going to full statelessness. And we basically argue that once you do that, like you get all these nice benefits, and those are worth it. But in direct comparison, in the pre-stateless world, I guess like you will lose something, like you will lose some performance because you do need to do this extra work.
Yeah, I think there will be, you made a good point, there will be regenesis of the leaves, I think, anyway, because if some contract code gets hot, for example, you wouldn't want to transmit that 24 kilobytes each time. So there might be some network level thing, maybe not protocol level, and that might be wise to do, or maybe protocol level would be wise as well. I'm just curious. Like, so Donkrot, can you confirm there could be regenesis for just the leaves with Verkle
What
trees?
does that mean, regenesis for the leaves?
Yeah, so you just don't retransmit because you have a witness. Okay. You have the leaf data. There are two blocks, one right after another. They both have the same code. Would you retransmit that
so
code?
You're saying two blocks access the same state?
Yes, the same leaves.
Right.
By leaves. Yeah.
Yeah.
Would there be a possible network or even consensus layer regenesis? Not for the intermediate nodes, of course, but just for the leaves.
Yeah, although I guess one other thing on this point is like, so this post that I published on ETH Research yesterday, this is the resurrection conflict minimize state bounding. Like the idea there is basically that it allows you to do regenesis like things, but without adding any kind of assumptions that say you can kind of poke into trees and store partial things with trees. Just because like the more we're making deep changes to what tree structure we're using, like the more you'd have to think about, well, what does this mean in binary land, and what does this mean in Verkle land, and what does this mean in whatever other land. Whereas like this approach that I recommended, like it does basically treat trees as a key value black box. So like that kind of approach would just allow the different parts of the research pipeline, I guess, to be more nicely separated.
And one of the questions, is a little discussion there in the chat, is, yeah, so what's being proposed obviously here is like going to Verkle and skipping binary trees. But in the future, in 5 years, when Stark is, developed and stable enough, then it would be actually going back to Stark binary trees. Is that correct?
Right.
Though it would be Stark binary trees using some like optimized hash function. So like like even if we did binary SHA-256 now, there would still be a big transition, maybe slightly less from like the direct engineering effort on the tree, but like you still need to somehow copy all that state over, right, into a completely new hash function that's still reorganizing the whole tree.
Backing up a bit, I think you already talked about this, but why will we pick 256 over, for instance, like 2024? What would the trade-offs be between like choosing? How do we choose our width?
Yeah, basically the challenge with having, like, the good thing about having higher widths is that you need fewer intermediate nodes. So like instead of 3 per data item, you might, or even 2 per data item, you could get away with like 1.5. And that would cut the witness size by a bit. The challenge is that it would increase proving time, because the proving algorithm that we've developed, it's basically for efficiency reasons, it just works over the polynomials in their evaluation form directly. And so if you have, if the width of those goes up by a factor of 4, then the cost goes up by a factor of 4. And so, like, given that it seems like proving time is one of the bottlenecks of the scheme, and witness sizes are already excellent. Like, it just feels like keeping it smaller is the better trade-off.
Makes sense.
I guess a lot of this discussion here has been oriented around how the Verkle tree is being used by the proposers to generate a witness for validation. I think we've had the previous discussions, and so I'm wondering if we can just bridge a little bit to what would this mean for light clients that are looking to get the state necessary to provide a witness with their transaction. What would that look like in a Verkle world?
Right. So having partial state needed to generate a witness yourself is one of those things that becomes harder in a Verkle world. And this is actually one of the reasons why, like, I think the roadmap that Dankred and I are recommending is to like not go beyond weak statelessness for like basically all the way up until until we do Stark binary trees. And so basically like you would not need transaction senders themselves to be generating witnesses.
Well, they get it from somewhere. Is the
Right. Or,
idea,
yeah,
right? So you basically ask your friendly proposer nodes in your local network or something like that. Like generating a single witness is really not expensive. So like it would be easy for someone to just provide this as a service. Like
in the current model, if you kind of have a get node data style retrieval, you can build witnesses yourself if you can retrieve things individually, even if you don't have the state. Does that map onto this? Is there a
so the thing
can you map that same? Yeah.
So actually there's a separate, right? There are transaction witnesses and block witnesses, and we will probably use different schemes for them.
I'm more talking about just like in general, like let's say that I want a proof about my account balance.
Okay, so one thing that you could do is you could just use get node data to just request the entire sister leaves. Like it's not going to be efficient, but for a single transaction, like it's only 32 kilobytes times n, and so if you're just trying to like compute the witness for one transaction, then that might actually be an okay trade-off, though not for a block.
Cool. So what I'm hearing there is that there is some mapping between Verkle trees, existing trees, and kind of how we, you know, there might be a hash that we can reference each node by, and you would look up all 255 siblings and then compute the proof yourself, I guess.
Okay. If you know all the siblings, you can compute it, yeah. But if someone is willing to send you all the siblings, then they might as well send you the proofs. I mean, it's not much more expensive to compute then.
Yeah, and this is where I'm gonna have to play around with it at kind of a, you know, toy level and see what makes sense.
So we've got about 5 minutes left. Maybe it's clear to other people, so it'd be good to just kind of outline it. It's not 100% clear to me of, you know, what are the concrete next steps in terms of, you know, making material progress here. And, you know, I don't love if the only answer is, you know, Don Crod, you know, you and Vitalik think about this for a while and come back to us. Like, what else can other people be doing here?
I mean, I think
my ask is for some simple test vectors that say, this is an example tree. These are the things that you should get if you build an implementation of this. Very simple, can be one vector even, but
right. I mean, like for the generic, for just some Verkle tree, we already have that, right? But the question is probably about a concrete one that would like that you could directly plug into each one.
Well, I guess what I'm suggesting is that if we had that, then it means that we can all kind of build, not all, but somebody who's really interested in this can start working on a fast implementation and that's, I don't know, it's like, it's the way that I learn about things. I'm not going to learn about, I've learned about as much as I can by reading else posts. And at this point I need to sit down and do some things.
But you have seen the proof of concept that I've written.
I have, I've been ingesting it. Yeah.
So how does that not provide a test vector?
I'm sure it does. I haven't actually run anything. I've been bouncing back and forth between
because basically things. you could use that as your, like, if you wanted to generate, like, make like a C implementation of this, you could test it against that. I think, like,
cool,
with some very minor adaptations. But yeah, I think like the best way.
Your kind of gut sense for, I know that the thing that you made in the research thing is not necessarily, I don't know, it's probably not perfect, but like, is that a starting point for somebody who wants to play around with this in the context of the full Ethereum state?
So as I said, there's like this thing about deciding whether we want extension nodes that has to be done, and if we do want, then that's a slight like complication. And if we don't want them, then we need to think about how we exactly restore accounts. Basically, then the account would probably be its own tree of some sort. And then I think, well, then there's a question about verifying rights. So like I would say like this kind of what I've done sort of should guide about 50 to 70% of the implementation, but then there are some gaps to fill at that point. And I think the best way is, so Guillaume I know is already working on this. So like I think we should like coordinate around that effort and make it happen so that we have like a concrete ETH1 example to play around with.
It sounds like another big missing piece is the trusted setup, figuring out how that would work.
So trusted setups exist. Obviously, we don't want to directly like use that on ETH1, but at least it's good enough for any kind of testnet, proof of concept, and so on, right? We can just use something that Filecoin has done or something like that. Yeah, but then afterwards, that is true. Like basically, I think like we discussed, so for ETH2, we will need that anyway, right? We have already decided that we are going to use KCG commitments for the data availability piece. So so we'll need to do a trusted setup and Ethereum 1. And I think we discussed that we, about half a year or so before we need that, we need to really start working on that and implementing that, auditing that, testing that, and yeah, then finally doing it. But yeah, I mean, it's a good point. That is definitely a major piece that we can't ignore.
Right. If all signs on sharding point to KCG still in the summer, I think that's kind of when we're going to put the pedal to the metal on getting that done.
How does
Joseph has his hand raised?
Yeah, how does implementing Verkle trees in Geth might affect the implementation of the merge in Geth? Because right now it looks like Guillaume's the only person, and just pointing out as well that Terrence from Prismatic is here, and he's got, you know, they have a lot of community members or contributors as well who are familiar with Go. Thanks.
Sorry, did you say Guillaume is the only one working on the merge? Or?
On the Geth side, it seems he's doing both the Verkle trees plus the merge.
Okay. Yeah, I think
so the merge work is probably largely stable, at least for the next couple of weeks on Geth side, working on a lot of specification stuff. And I do hope that as we get that specifications out and begin to have a regular cadence on a call, there's many more people than Guillaume working on the merge from multiple clients and maybe another member of Geth. But I won't speak for Guillaume. Yeah.
Yeah, I mean, it does feel like more resources on that would be helpful, yeah, if we can find anyone. Like, I don't think like the Verkle tries themselves will be that complex, but I think all the stuff around making it work will definitely be, yeah, a lot more.
The last question in the chat also seems helpful here from Pooja. Like, where in the roadmap does this tentatively look at?
London feels a bit close, right? Like because like
London needs an EAP in like the next 2 weeks. So unless that's the level that it's at.
No, definitely not London, I would say. Well, I don't know. I mean,
this is you start colliding with merge work towards the end of the year. And so at a certain point, like if this needs to get in before merge, then you probably delay merge a certain amount so that you can ship this.
I would actually recommend doing it the other way around. I don't know. My feeling is we should do the merge and then get this done. I don't
Yeah,
think we
yeah.
should do both at the same time. Like that's.
I mean, at a certain point, the resources would be competing. So we do need to make a call on
Yeah.
one or the other.
Yeah.
Priority.
Also, wouldn't it theoretically, at least if both are ready on a similar timeline, be preferable to do the tree migration before the merge? Because that
Yes.
would kind of, okay.
I guess so, yes. I guess I don't expect it to be available and ready before we're done with merge work. I don't know. Danny, do you have a?
There's a lot of moving pieces at this point. The
Right.
trusted setup might end up being the bottleneck if the engineering stuff's done, but I don't have a good feel for the implications that are like how deep this goes into the stack with respect to databasing and things like
Right.
that. Like, it's the kind of thing that might like affect everything, and in that sense, it might take some time. So I think we just need to kind of push forward on the R&D on both and begin to refine specifications and move things to production as they're ready.
Quick one on the trusted setup. So can that reuse any of this perpetual powers of tau or any of that work, or is it a new one?
It absolutely could. Though, well, okay, so actually I think we have like two routes for it to go with a trusted setup, right? Like like the distinction that I see is basically, do we make a big one or do we make a small one? Like because Kate commitments for an ETH2 only require a trusted setup of size like 2 to the 15, or even like we can maybe 2 to the 19 if we want to kind of go up a bit, right? And be able to survive future increases in block size. Whereas the setups that are meant for snarks tends to have sizes that are like way into the millions. And if you have sizes that are small, then like, as I mentioned, like you can just stick it in a browser, right? And that just greatly increases the number of people who can participate. So we could even just like start with the perpetual powers of tau and like add even more people to it if we want.
Around how many people are we looking to participate? Because that PPOT, I think, I don't know if it's gotten to 40 or 50 people already.
Right. My personal preference is definitely a lower bound of 200, but.
And what size do you need for the actual Verkle trees if you put the sharded data aside?
Oh, for the Verkle trees, you just need your size 256.
Yeah, I think the bigger, like, and the Verkle trees, once you've done them, like you won't increase them, right? Because that would be a huge change, and then you can make a new trusted setup anyway. So the bigger constraint is really like data availability, where you may want to increase block sizes, for example.
This was great. Thank you, guys.
Yeah, this is really helpful. I think everybody got a much better understanding of the implications of Verkle trees. I will get this recording out and send that out by email to everybody. And I think the next meeting is likely going to be our regular monthly meeting, not a topic meeting, if I'm looking at the calendar correctly. So look forward to seeing everybody there, unless there's anybody else with any final things that came up in the last minute in their mind. Nope. All right. Thanks, everybody.
Cool.
Thank
For participating.
you, everyone.
See you
Yeah.
guys.
Bye.
Thanks.